Okay, so this is our third video dealing with topic 2, and we're going to be talking in this particular video. We're going to be talking about hash algorithms and key management. All right, so we talked in the previous section. We talked a bit about encryption. So as we talked about the encryption, one of the main elements of encryption is this idea of keys and key management. So what we're going to talk about here is going to be some of the characteristics of, basically what we call hashing and hashing algorithms. We're going to talk about message authentications. You know, what are these hash functions and kind of what do we use them for, and how do they relate to cybersecurity? And then also some key techniques, encryption key techniques. Remember, we had talked about one of the big challenges with encryption is, the management of the keys. So some of the different techniques that are out there with that. Okay. So with that, to start off with, we talk about this idea of data, the vulnerability of data, when you could, and part of what a database will do, part of the job of the database is to protect the data, to ensure that it is maintained, it is secured, it is updated in appropriate fashions. All right. So as long as as long as the data is in the database, we have the mechanisms of the DBMS that's going to do that for us. Okay. But however, data doesn't always sit in the database. A lot of times, what will happen is data will be transferred across networks, and it's the most vulnerable part is when it runs across an untrusted network, like the internet. The internet is, by itself, when its original design, is inherently untrusted. So basically, there was no security that was built into it. All the security mechanisms that we see in, on the internet communications, are stuff that has been really added later on after as time has gone on, as the need was better understood about the need to protect data as it's moving. All right, so there's a question of what we call data at rest. So inside of a database, that's data at rest. And then when data is moving, we call it data in flight. So there's a risk, actually pretty high risk, of data modification occurring during transmission, which could impact the integrity of the data. All right? You can go in there and, people can mess with it. All right. So part of the challenge, part of the thing we're always worried about is making sure that data can move from point A to point B and get there, and the data that got moved is correct. Right? So we have techniques. There's a number of different techniques that have been developed, as we call it, message authentication. Right? And what its purpose is, it makes sure that data has not been tampered with during transmission. So it validates the integrity of the data, so that what was received was what was sent. In addition, it also validates the sender of the data. Right? So that it is, if we're receiving a message from somebody, that somebody is that somebody. All right? It's not somebody pretending to be that somebody. And then finally, it identifies the uniqueness of the data, to making sure that the data is, it is the correct message. It's coming from the right. It's not a duplicate. It's not something else. It is that particular message that was being transmitted, the data that was being contained within. So the idea of a hash function. All right. So what a hash function is, it's really just an algorithm. It's a programming an algorithm, usually implemented through computer code, that will run the input data text through this algorithm and produces an output value, a unique output value that's derived from the input text, and we call that the MD value, the message digest value. All right? So basically, what it is I got a message, I analyze it and kind of look at the profile of it, based upon different characteristics of it, and we'll generate this MD value. And what we do is we use these hash algorithms to authenticate the messages and verify the integrity using this value. So what happens is I create a message, I run the MD value, I create an MD value for it, I send the message along the way, and then I also send, maybe through another communication stream, I send the MD value. and then the receiving message, the receiver of the message can then match the received message with the MD value, calculate the two, make sure they are correct, make sure they align correctly. All right. So the idea is though that so there's a bunch of different algorithms, and so there's a couple different ways you can get function. So some of the characteristics of this is you want to make sure that the data can be of any length. The output MD value has to be a fixed length, so you don't just you don't arbitrarily. So you want to create a number that you can calculate to. All right, can be calculated across any input value. We say the function should be collision free. So what we mean by collision free is we don't generate dupes. All right, so we want to generate a unique MD value for each input data stream, and then finally, we want to make sure there's a one-way function supported, so the input data cannot be guessed or derived using that value. So you don't want to be able to take the MD value and go back and establish characteristics of the data that was used to generate that number. All right, so it's a one-time function that is arbitrary. Basically, it reflects, the construction of the data, but doesn't give any clue of exactly what the data looks like. So the algorithms, a couple different types of algorithms out there: MD2, MD4, MD5. So it's been around a while. MD2 was the original 8-bit processors and pads. So basically, a lot of that stuff was, first generation PCs and things like that. Using 16-byte checksums and then 128-bit MD value that was calculated. That was followed on by MD4, right, which was actually supported 32-bit processors. So it was, but the problem was, one of the problems they had was it generated a lot of dupes, so a lot of collisions. So what they did is MD4 was replaced by MD5. So it has the same, basically, functionality of MD4, except it doesn't generate duplicates. Okay. So a couple others out here: Haval, 1024-bit input blocks combined with variable length, 4 or 5 rounds of operation. Okay, so SHA1 these are new, some of the newer hashing algorithms that are out there now. Okay, so SHA1 was developed by NIST and National Security Agency for digital signature standard. All right, so the idea is to create a standard that you could analyze take an input, analyze it, and generate a digital signature, as part of encryption. All right, so the idea of in creating 120, 160-bit MD value. All right. One of the things it actually is free from collisions, which is always an important thing. The fewer collisions, 0 collisions is obviously your goal. Fewer collisions than more collisions is clearly what is what we're looking for. Then we have SHA3, which is really a new hash algorithm. All right, which is really kind of leverages new advances and new technologies that have been applied in this area. So how do people attack? How do hackers attack this stuff? So there's a couple things they're looking to do. One is obviously a collision. So obviously, multiple unique inputs generate the same value. If you increase the bit size of the output hash, the risk of collisions decrease. So basically, if you increase the space, basically the size, the odds of you running into a collision scenario drops. All right. Another attack, aliasing, restarts it, the hash algorithm through any input, make it easier for the attacker to create input to try to create the hash values. So really, from an attacker's perspective, what their objective is to create an MD, a fake MD that looks legitimate. All right, so in fact, to be able to create a hash and be able to and then attempt to foist off these fake MDs as real MDs. There's a third type of attack, kind of an interesting thing called the birthday attack, basically used to find collisions in hash algorithms. Referring to probability that two entities in a group can share a common characteristic like a birthday. All right, and the MD5s, SHA, are designed really to find and prevent collisions. So collisions are bad. All right. Message authentication codes. One of the well-known attacks we have is what we call a man-in-the-middle attack. All right, where what will happen is two parties will be communicating, and a third party will intercept the message, read the contents, and then pass it along the way. From a perspective of the two parties, they don't see anything happening. So the idea is these man-in-the-middle attacks. And what happens is hash algorithms that generate non-keyed MD values, they're prone to be able to do this. So what will happen is you intercept the associated MD value, you change the message, you create a new MD value for the fake message, and you send it along, and it looks like the MD value matches, so it believes the message was not modified in transport. Okay, which is not a good thing. Right? Secret random key, the way you get around that is you create a secret key. So you create a different type of message authentication code, a MAC, and embed it into the message. And it can be used to validate the sender integrity and uniqueness of the message. And it's invisible to the man-in-the-middle attacker. All right. So say for example, a man-in-the-middle intercepts the message, kind of generates new values, passes the message along, and it matches it up. And what will happen is the receiver will take that information, those MD values, and then match it up against the message authentication code and see. And if that doesn't match up, then obviously it'll be rejected. Obviously something had been tampered with. So right now, digital signatures are really one of the main means by which we perform authentication, especially through the internet across the network. All right. So this idea of digital signatures and certificate authorities. All right. So the idea is that digital signature is going to provide the integrity, authentication, non-repudiation for a message. All right. And basically run the algorithm on a message content encrypted with a private key. All right. That's a digital signature. A CA, a certificate authority, is a trusted third party that basically what you do is you go to them, you buy a certificate from them, which is authenticated by them, and you can use that as an alternative to creating your own messages or creating your own certificates and authorities. All right. And there's some very well-known ones out there. So there's a lot of CAs that are out there, which and this is a pretty well accepted approach. One of the things about if you're a certificate authority, the holy grail is obviously protecting the integrity of your certificates, to making sure that does not becomes compromised. Because quite frankly, if your stuff gets compromised, then every person who is using your authority as a basis for a digital signature would be suspect. So obviously, you really, CAs, protect that, go to really large degrees, extensive degrees to protect the integrity of their certificates. Digital signature algorithm, it's really just for creating a digital signature. All right, kind of works. It does it can create signatures, uses secure hash algorithm 1, SHA1, creates a message hash in which the secret key operates. All right. So you verify the signature by you recompute the message hash using a public key to decrypt the signature, then match up the results. All right. Just another technique in proving that whoever had sent that message was who they say they were. All right. Here's just kind of a diagram about what these things look like between private key and public key. So you have a private key, creates so our person here, Mary, creates a text message, encrypts it using Mary's private key. Well, I guess it depends on the way you start. Bob's message, we would encrypt it using symmetric cryptography, encrypted messages, decrypted with some symmetric cryptography. So this is going to be a public key, a symmetric. So that's going to be the same key. Or, so this path right here deals with symmetric. So they both have, there's a shared key between these two, between Bob and Mary. All right. And then down here, we have a public key, private key. All right. So what will happen is the messages will be encrypted using the public key. Or excuse me, it will be encrypted using, depends, you can use it, you encrypt using the public key and then you decrypt using the private key. I think that's the sequence. Encrypt with public key, decrypt with private key. All right. So some guidelines with PKI, public key infrastructure, a couple things, a couple guidelines. Key should be long enough to provide security. The key transmission should take place over a secured network. You don't want to send that. You don't want to send keys over, over unsecured networks. Key generation should use all of the key spaces. You don't want to do this half. You don't want to create half a encryption or encryption off of a half a key. All right. New key lifetime should be short if you're using it for sensitive data. The longer a key exists, the longer the probability that it will ultimately become compromised. Keys should be backed up, and then finally, keys should be destroyed when not in use. So this is some best practices associated with this. And that is everything we need to know about hash algorithms and key management.